On behalf of Evoke 3D, Entopology, HP 3D and AM Technologies, welcome to our webinar on digital design, materials and post-processing in orthotics and prosthetics. For those who attended our previous session, welcome back. We appreciate our global audience and presenter lineup, especially those who have joined us early in the morning. I'm Joe Carmody, Managing Director of Evoke 3D, and I'll be facilitating today's event. This webinar dives into specific topics requested by our audience, following our previous O&P session, which is now available on the @Evoke3D AU YouTube channel. If you're interested in a broader overview of the O&P digital workflow comparison, I recommend checking it out. We'll provide a link at the end. Before introducing the agenda and speakers, just let me briefly introduce Evoke 3D and our mission. Founded in 2013 in Melbourne, Australia, Evoke 3D aims to deliver high-quality additive manufacturing solutions, including machines, materials, support and software. We offer end-to-end solutions from digital file preparation to 3D printing and post-processing, covering the entire process from art to part. Over the last 11 years, we've been involved in the digital transformation of various industries, including dental, orthodontic, audiology, jewellery, eyewear, and orthopaedics. The application that excites us most is orthotics and prosthetics, which delivers life-changing patient outcomes. We recognise the complexity of O&P and the expertise of the practitioners on this call. We hope this webinar provides valuable insights or sparks new questions on how digital manufacturing can enhance patient outcomes and productivity in your practice. Today we'll have 3 presenters. I'll provide a more detailed introduction before each section, but here's a quick overview. First up, Simon Bartlett from Evoke 3D, who will go deeper into prosthetic socket design workflow with Entopology software. Followed by Clara Remacha from HP 3D, who will present on design and material selection. And last but not least, Sam Martin from AM Technologies will cover vapor smoothing, post-processing in O&P, which is now well established as best practice in the industry. At the end, we'll have a Q&A, so if you could please put your questions in the Q&A chat box at the top there. We'll endeavour to answer all of them, time permitting. So, introducing Simon, who has over 25 years of engineering and management experience working in demanding roles across 3 continents with some of the world's largest multinational companies. Since completing his studies at Swinburne University, he has worked in both design, development and management engineering roles. Simon helps organisations transform the way they work using lean manufacturing methodologies to drive process efficiency improvements, build high-performance teams, and adopt the latest advanced manufacturing technologies. The result, increasing shareholder value by setting a clear vision and delivering on that vision. Over to you, Simon.
Thanks, Joe. I guess I sort of consider myself as partly the entree rissole to our international main course, which is to follow. And I must echo Joe's sentiments too. I really appreciate both Clara and Sam joining us, and we're very, very fortunate to have international representation today. A little bit more about what I'd like to try and go through today. So really, I'm going to go a little bit deeper into Entopology and how it complements existing CAD design, and talk about the performance improvements that it can and how it can value add. So we'll talk a little bit about what is Entopology, but then also go a little bit deeper into the relevance of Entopology and O&P. And hopefully, if anyone wants any further information, of course, they can reach out to us after this session and we can go even deeper and do some live demos. But starting with what is Entopology, and I guess how does it differ to existing CAD or traditional CAD? So CAD software effectively originated back in the mid-70s. And it hasn't really changed sort of too much, but what CAD does is it effectively uses mathematical formulae to describe a surface. So it's surface modeling. So, and the way that it sort of stitches parts together. What it doesn't do is it doesn't look at the internal volume of a part. So I can use that to predict a point on or determine a point and describe a point on a surface, but in terms of that internal volume, that is considered space. So moving across into entopology and implicit modelling, sorry, just go back one tick, Shika. So what we're effectively doing though with entopology is instead of using formulae to describe a surface, we're actually using functions to describe a volume. And so what this does is it gives us greater control. With that function, what we are able to do is effectively we either have a negative or a positive. If it's positive, it'll be contained inside of that volume, that boundary. If it's a negative, it's outside. So it's a lot easier and simplified and gives us greater control over that volume. Next slide, Shika. So what does this mean? So with greater control over your part or your design, there's really sort of three main attributes to entopology. So one is using fields and ramps, we can actually control that internal structure. And so whether we want to do light weighting with lattice structures, etc., we have a lot more control over our part, which makes it a lot better in terms of, as I said, sort of reducing weight, reducing material, etc. So it gives us that improved control. Another attribute of entopology is what we call field-driven design. And so that's using external packages like FEA modeling, etc., looking at flow analysis, and we can bring that in as a design driver into entopology. Like the bike seat that we're showing there, we're using a pressure map to change the internal structure. So we can actually vary the way that the part performs based on an external source. Another one, or the last but not least, which is actually really relevant to what we're going to be talking about today, is looking at automated workflows for clinicians, etc. That are actually on the during the presentation. You'll see that, for instance, if you've got one customer, etc., having automated workflows, it really does allow you to scale, particularly for those repeated design tasks. So where does it fit? So really, as I said, so entopology sits alongside traditional CAD design software. And so your output from your CAD design will become the input to entopology. Also for simulation results, as I said, if you're using FEA work, etc., if you're using material properties, all of these can become inputs, which then entopology can optimize your design for your manufacturing process. Now, of course, we're a 3D printing company, so this is one that we're focusing on, but it really does help you to leverage what you can achieve with 3D print. And remember, what we're trying to do is get away from just repeating and replicating what we've done previously with, let's say, with layup tools, and really value add and exploit the attributes which 3D print can offer. And so that's either through optimizing geometry, looking at meshes, etc., and also looking at manufacturing data. And our output, not only can we take it directly into a 3D printer, but we can also use it as as an input and take it out as a CAD model and put it back into our CAD design. So we can have this evolution and this revolution of a design cycle. Okay, so the main applications that we're seeing. So lightweighting is as we've sort of just touched on, if we have better control over the volume itself, we can add lattices, etc. Thermal management. So we're looking at heat exchangers. What we're seeing here might be hard to see is instead of using a lattice, using a TPMS structure. So we're using and controlling the surface area for better transfer of heat. That could be heat, it could be airflow, it could be water flow, it could be pressure. Mass customization. Now, this is particularly useful when we're looking at O&P, when we're looking at volume and scale. So, of course, mass customization, mass personalization. So when we've got automated workflows, our variables only really become our biometric data as an input. Industrial design, using topology and using maybe external drivers, etc. We can obviously use it as a design tool, maybe not for the primary design, but we can obviously add value by using it too. Architectured materials, this is particularly valuable when we're looking at digital foams, like we saw with that seat, and then manufacturing tools as well. Bringing that back to O&P, how can we apply topology? Well, here's a couple of examples on the next sort of couple of slides. For instance, what we see here is a midsole. Now, on the left-hand side, you'll see a midsole, which has been designed in our CAD software. And when we talk about field design or field-driven design, we've got two inputs in this particular application. So one is looking at the plantar pressure input. So looking at the pressure, the physical pressure that we are applying to that sensor. And so this gives us that digital output, that color map that you see. And then below that, we've got another input that we can have too, which is actually the biometric data of the patient. And we can actually bring those two together. I've actually got the example that you see on the screen. Hopefully you can see that too. So using that pressure map, hopefully you can see that we have used that as the driver for a Voronoi unit cell structure. We are using that, as you can see, in the red areas where we've got a less material, which gives it that sort of flex. And in the blue areas, you can see that we have a higher density mesh structure. And then not only that, we can add the biometric data from the patient too. And so any of the clinician's inputs, we can also drive that design as well. So it's actually sort of doing two functions. So not only can we improve the gait, but we can also improve on the form and fit to the patient as well. We can also look at if we're looking at sockets, and this is another example. So again, on our left-hand side, this is our traditional input from our CAD software. And so that gives us the volume and the surfaces that we need to work with. So we've taken the scan, a patient scan, and inside of topology, we've applied some forces to it. And that gives us this, and this is where we're using finite element analysis. We have wrapped it in a mesh, and you can see there where areas of high strain and stress are shown in red, areas of low stress, etc., are shown in blue. Now, we've used that scan data and used that FEA work to actually drive the design of the mesh structure that you see just as an output. For instance, why would you want to do this? One is actually for lightweighting. We could, instead of having a socket which is, let's say, 4 mil thick, we could get the same mechanical performance if we had a socket that was maybe, say, 2 mil thick, but we added a mesh structure to the outside, which gives it additional strength. Then you can see that the gradient of that unit cell varies based on the internal driver, or the driver, which is the finite element analysis. And then on the far side, this is where you see effectively the final part. Okay, so before we go into sort of probably having a little bit further deep dive into topology, this is one of our customers and one of our advocates for topology is Ability Made. What they have been able to do is they're looking at automated workflows because of the volume that they need to do for their customers. The key takeaway for this slide is they have been able to take their design time down to sub 10 minutes for an AFO. So which is a design compression for them of over 300%. What does this all mean? So one, apart from time compression, one of the most important takeaways too is Ability Made is registered with the TGA for Class 1 for design and manufacture. I'm not an expert, but we know that the TGA at the moment does not regulate the design for AFOs and for sockets. They do for the hardware, but not for the socket or the AFO itself. But it is coming and it will come. So Ability Made, because they are design and manufacturing responsible, they have future-proofed themselves. And how that works and how does that tie back into topology? So with automated workflows, they know, or they've been able to show, that their quality control is improved, but they have control over their process from input data, from their scan data, all the way through their manufacturing process. And with automated workflows, etc. But also too, what they've been able to show is as their skill base is increased within topology, they can actually add complexity without adding additional CAD and resources or design time. And not only that, they've been able to improve their development capabilities, but they've also been able to, with the time that they're saving, actually release more product. Because what they can do is, within topology, is they can take a number of their workflows and they can mimic those across other different applications. So effectively, we're still scanning biometric data and having an output, but they've taken it from AFOs to splints, etc. So they're able to replicate these workflows. There's an adage that says never work with animals, children, and never do live demos. So this is why we're not doing a live demo today, but more than happy if anyone wants to reach out. Happy to do a live demo about topology and maybe the workflow that we'll sort of touch on here. But as we said way back on the third or the fourth slide, topology is all about the inputs and the outputs. Now, the inputs to generate this AFO that you see here, and this is a very simple AFO, and it probably doesn't even look very good to a lot of the people on the call. So the inputs that we take, so we take the scan data, and what you see, the other inputs that we take are these trim tools. And these trim tools may be something which you generate in an external CAD package and then bring them in. You know, they could be standardized, they could be patient specific. But effectively what they do is they allow us to trim the design based off our scan data. And then the other variables which I've just pulled out there is the clearance to the skin, whether the thickness of the AFO. So this all can come down to, you know, the clinician's requirements, you know, they can put into the design. I've just taken them out as variables in this workflow. The distance, we've actually got a ramp up there for easy ingress and egress. It's hard to sort of tell, but we've got a ramp there at the top of the AFO, and even the perforation size and the density of those perforations as well. So these are all variables. If I come along with the next patient, and this is a design that I'm happy with, all I need to do is I need to make sure that my scan data aligns with the scan data that I've got here. If that becomes my variable as my input, to generate this AFO would probably take me around about between 60 to 75 seconds. But as I said, more than happy to walk through this and do a live demonstration with anyone that's interested. And please, you know, obviously you can reach out to me after this sort of session. But that is topology basically in a nutshell. So what I wanted to sort of stress, really what it's about is that automating workflows and improving on that design complexity, which we know for 3D printing comes for free. That's me done. Over now to the main course. I really appreciate Clara joining the call because I know she's busy, but let's crack on. Thanks, Joe.
Hi, Simon. Thank you for that delicious entree. Hopefully that's whetted our appetites, if I can just run with your analogy there. But allow me to introduce Clara Remacha. So based in Barcelona, Clara is the global 3D polymers project manager for HP's 3D printing and digital manufacturing business, where she's responsible for defining and delivering the future roadmap of products for HP multi-jet fusion technology, hardware, supplies and services. So a very senior position there. A core member of HP 3D's printing digital manufacturing business since its inception, Clara was part of the team who launched HP's first 3D printer and has spent the last 7 years helping customers and partners turn ideas and designs into real 3D production applications. And that's across multiple industries, including industrial, automotive, medical and consumer goods. Clara holds a bachelor's degree in industrial engineering from UPC Barcelona, an international master's in management from EADA Business School, as well as an MBA from the University of San Diego. She's also an athlete who competed professionally in track and field for FC Barcelona for several years. So very talented. Thank you, Clara. I'll hand over to you.
Thanks, Joe. So hi, everyone. Good morning, good afternoon, depending on where you are. What I'm going to present is a bit of a deep dive on the materials section applied to orthotics and prosthetics. And I thought I'd start with the conclusion. We have a big portion of our customers that are focused on O&P applications, sockets being one of them. And when you look at what materials they are using, in the end, we have a broad range of materials from rigids to elastomers. But if you look at these specific applications, there are, for a socket, two main categories of materials that are used. So for the liner, that's because of the comfort requirement that always is an elastomeric material. And what we see being used the most is mostly TPUs. So we have TPUs and TPA. In this application, because it's of course in contact with the skin, we see TPUs being used the most. We have TPUs from BASF, TPUs from Lubrizol with slightly different properties. So that's more of a customer preference. That's for the liner. And then for the socket in itself, that requires a rigid material. And on these, the ones that we see mostly being used is either PA12, PA11, and PP. You can see here the properties in terms of like tensile strength, modulus, elongation at break. They are slightly different materials, but honestly, we've tested all of them and they all work for the requirements of this application. So when you try to ask people why do they use PA11 or why do they use PA12, why do they use PP, it's actually a geographic and customer preference. So we see PA12 being used a lot more in the US. In APJ and Europe, we see PA11 being used most. PP is growing a lot. So really, it depends on the specific application and the specific customer. But all those have properties that actually match the requirements of this application. Now, one thing, and I'll touch at the end of the presentation a bit on waste and sustainability, but one thing that differentiates these materials is the refresh ratio that we have. I included here, but PP is the highest recyclable material that we have in our portfolio. And then PA11 is 70-30. These ratios, basically what they mean is for PA11 being 70-30, this means that you need to add, for every job that you do, you need to add 30% of fresh material. Versus in PA12 that you need to add 20% always of fresh material, the rest is recycled. And then PP, you need to add 10% of fresh material every time that you do a job. Now, if we move to the next slide, what I thought I would cover is what is the first question that a customer that wants to move from traditional manufacturing of sockets to additive manufacture needs to answer, no? And the first question is it safe? In the end, it's a different manufacturing process, so you need to qualify the application and this applies to all applications in all segments. So the first question is it safe? So in order to demonstrate this, we did a study in collaboration with Quorum Prosthetics, and we manufactured a traditional socket made out of carbon fiber and then same design with MJF. This study was done with PA12. I will show a bit of data of the other materials later, but just to explain a bit the methodology of the study, we basically looked at two things. One was static testing, and that's the maximum force that the socket can withstand. And the second one is dynamic testing, fatigue testing. So if we go to the next slide, when we did the extreme testing, here you can see a bit the results. The left graph is the MJF socket. The right graph is the traditional carbon fiber socket. I added the line so that you are able to compare both graphs at the 3,000 newtons force. But basically, when we apply the static force, you can see here in the curves that basically all the MJF sockets that we tested on PA12, they surpass the 3,000 newtons force, and they all get to about 4,000 newtons, more or less. There was the one that you see in red, that was a bit of an outlier. We believe that there was something wrong in the measurement, but for all others, you see that all can reach 4,000 newtons of force, which when we work with this customer, their safety factor is basically 2x of the body weight, and that was surpassed. So in the end here, what's the conclusion? No, in terms of static extreme force, the additive manufactured socket is as good or actually even better than the traditional carbon fiber one. And then in the tables, you can actually see the specific numbers for the different sockets that we tested. So that's a static testing. Now, if we move to the next slide, we can see the results on fatigue testing. And the test that was done in here was that every 250,000 cycles, we would increase the force by 500 newtons. So we were repeating this process, and then when did the sockets fail? Both the traditional and the MJF socket failed at the step of 2,500 newtons of force after more than 800,000 cycles. So again, what's the conclusion? The conclusion is that when you put it dynamically in fatigue testing, both sockets actually failed in the same step. So it can be a comparable performance in terms of safety. Now, if we move to the next slide, this test that I just explained was done with PA12. We have another customer in Europe that probably most of you know is Invent Medical. They use a different selection of materials for their sockets. They use PA11 and TPU for the liner, but they did a very similar testing. So they did static testing. And in this case, because PA11 has slightly higher mechanical properties than PA12, this reached almost 5,000 newtons of force in the static testing. And then on the next slide, you can also see the results of the dynamic fatigue testing. This was slightly different in terms of methodology than the one that I previously explained. They didn't change forces every X amount of cycles. They just had a constant force of 1,200 newtons, but this surpassed actually more than 1.5 million cycles. And their requirement was 4x the body weight. So in the static testing, so that was also passed. And in the end, what I wanted to show with this testing is that the most important question when you change the manufacturing process is it safe or not? And both studies show that the MJF socket surpasses the requirements in terms of safety, so it can be used. And that's the first step. Now, on the next slide, once you have checked the box of safety, you have to look at what other benefits using additive manufacturing can bring you in terms of patient outcomes. And I use this socket because it's a very nice representation of these other benefits, but we're talking about design flexibility, things that you can add, and Simon was touching on this earlier before, things that you can add that make the design more complex. This all comes for free. Breathability is also something that is a benefit for the user. Lightweight, that's also a benefit for the user. And in the end, if you sum up all these things, this all leads to higher device compliance, which in the O&P world, that's what basically you're looking for. Now, this is all applied to sockets, but the same things that I explained can be applied to a broader range of orthotics and prosthetic devices. So on the next slide, you can actually see the applications that we see. As I said in the beginning of my presentation, we see a big portion of our customers now focused on O&P, and that's from OEMs that buy the equipment, the printers to do these devices, to parts providers, that a big portion of what they do is actually serving other customers in the O&P space. So applications we see, of course, insoles, that's the biggest, but we also see braces, AFOs, DAFOs, cranial helmets, fairings for prosthetics, the sockets, obviously. We're starting to see more and more of scoliosis braces, prosthetic arms. So there is a wide range of applications. Now, the last thing that I wanted to touch on was sustainability. When you compare, I mean, there's one thing, first is safety, then what other additional benefits you have from using additive manufacturing, but then sustainability is also an important point. So if we go to the next slide, I wanted to touch on a couple things. One is waste. When you compare traditional manufactured orthotic device versus an additive manufactured device, the main difference is basically on traditional, you start from a block of material and then you're subtracting material. So the waste that you generate in the process is high versus additive manufacture, where you're basically only fusing the material of the final device. The difference in waste from these two processes is very significant. I'm not saying that the additive manufacturing process does not generate waste, because it does. So I wanted to also touch a bit on this. What is the waste that is generated by the additive manufacturing process? It really depends on the packing density that you're able to achieve and the refresh ratio of your material. So when I started on my first slide, we had different refresh ratios for the 3 rigid materials, going from 70-30 to 90-10. If you have a really high packing density, for example, for insoles, they are reaching packing densities of 12-15%. Then if you go to PA11, that is 70-30, you're almost generating very little to no waste. But if you go to an application like a socket, where it's very difficult to actually nest different parts, and that's for socket, the typical packing density is 5-6%. Then if you go to a material like PA11, you're generating powder waste that you need to do something about it, versus using polypropylene, which you're basically not wasting any material. So you need to, when considering the waste in additive, you need to take into account the relationship between your device, packing density, and refresh ratio. Once you have fixed that, if you end up generating some waste in terms of powder that you cannot reuse, I also wanted to touch on recycling programs that we are using. We are working with the main material suppliers, Arkema, Evonik, BASF, and basically what they are working on is taking waste powder, but also waste parts, and turning them back into pellets for injection molding. We've been actually in our lab in Barcelona, all the waste powder and waste parts that we generate, we're using these recycling programs. And just last year, we recovered 25 tons of material that we then turn into pellets for injection molding. So those programs are already available. And then the last thing that I wanted to explain is also touching on sustainability. When you decide which material you want to use, another criteria that you can use is also what's the carbon footprint of the final part that you will be producing. And to understand the carbon footprint of the different materials, if we move on to the next slide, I'm going to go pretty quickly and very simple, but what things you need to take into account to calculate the carbon footprint of your final part, depending on the material. There are basically 3 things. The first one is each material has an LCA, and that's coming from the raw material in itself. So you can see in here, that's the LCA data from our material suppliers, just the material in a raw form. And you can see here the comparison. So the lowest LCA from our raw materials is PA11. Why? It's because it's bio-based. So that already starts from a low carbon footprint. Now, the next step, if we move to the next slide, is you need to add the refresh ratio, because that's the amount of material that you need to put in our process and in your process. Here you see that the differences of the materials are more balanced because PA11 started with a -50% versus PA12, for example. Now it's at -20%. Why? Because in PA11, you're using a lot more fresh material. It's 30% versus PA12, that is 20%. So that's the second thing that needs to be input in this calculation. The third thing, if we move to the next one, is the energy that is used into the process. In the end, a printer, you could make an analogy, a printer is like an oven. You're fusing the material and then cooling it down. There's a lot of energy that is put into the system, so that needs to be taken into account also for the carbon footprint. What depends, the energy that is put basically depends on what's the melting point of the material. PA11 is the highest melting point of the different materials we have in our portfolio versus TPU, that is the lowest melting point, and therefore it uses the lowest amount of energy. So that also needs to be put into the calculation. And again, on the energy, the carbon footprint of that part will depend on where in the world you are basically manufacturing. If you are manufacturing in France, for example, where the grid comes from renewable energy, that portion will have a lower impact in the final calculation of your carbon footprint. So that's something that you need to take into account as well. And then when you put all these three things together, if we move to the next slide, you would have a comparison of the different materials, what's the carbon footprint of the final part. Now, these numbers, don't take them as the single version of the truth, because the energy portion, I think it was taken with the energy grid in Spain. But if you are somewhere else in the world, these percentages might change. In Spain, for example, you can see that PA11 still has the lowest carbon footprint. But again, as I said, if you're doing this in another country, this might be PA12 or PP. You can see that all the rigid materials, PA12, PA11, PP, they have very similar carbon footprint. So that's, I just wanted to touch base on this because it's another decision point that you can use in selecting the material that you will be finally using. We have recently introduced a carbon calculator. So if you are interested to know exactly what the carbon footprint of your parts are and have a material comparison in your specific country, that's something that you can reach out to Simon, and then he can come to our application engineers and we can have a joint calculation on this. And now I'm going to pass it to Sam to talk about post-processing.
Thanks, Clara. That was very enlightening. Yeah, I think the practitioners on this call who, obviously work with traditional manufacturing methods would be very aware of the volume of waste that can be generated from those processes. It's great to see what HP is doing there with the carbon tool, etc. So please reach out to us if you'd like more information on any of the content that Clara's presented there. Now, I guess we're moving on to the dessert course with Sam Martin. So Sam's the Global Application Engineering Lead for AMT, AM Technologies Post-Pro. Sam's based in Cyprus, and Sam is the Global Application Lead. He has a degree in engineering and a comprehensive technical background across many industries. Since joining AMT in 2021, Sam has been an integral part of the company, playing a pivotal role in its development and growth. As the leader of AMT's applications activities, Sam oversees all aspects of the company's customer onboarding and their product development, driving success and innovation across international markets. So I'll hand over to you. Thank you, Sam.
Yeah, thanks very much, Joe. It's really interesting to hear a bit about Clara's and Simon's background as well. So thanks for that, guys. So hello, everyone. Welcome. So I'll be focusing on, obviously, the post-processing, primarily for the O&P world, of course, to look at the part quality and patient care that you can expect to see using our technologies. So some of you may or may not have heard about us. So I'll give you a brief overview of who we are and what we do. So we were founded in 2017 with a global leader for automated post-processing solutions. And our aim is to provide an automated finish for every 3D printer material and have a viable manufacturing technology for all. So as a company, we have over 60 employees spread across the US, Hungary, and the UK, and we have more than 400 systems installed in 37 countries. With the reseller network, we're able to hit a lot more areas. So, for example, in Australia, we have Evoke 3D handling that for us. On the right-hand side, you can see a quick summary of some of our partners, the investors, and also the awards we've received in the last 7 years, just to give you an idea of who is behind us. Next slide, please. What do we sell? What do we do? What are post-processing solutions? So there's three main ones that we focus on. These are depowdering, surface blasting, and vapor smoothing. So they're all designed to meet specific needs for customers, whether that's in the medical, the dental, or the automotive industry. So I'm sure some of you are already aware of these, but I'll give you a quick rundown of each just in case you're not. So the first one is depowdering. Essentially, this is once the parts are removed from the build cake, we'll depowder the parts in the depowdering machine, and that will remove any loose powder, leaving you with powder-free parts to go on to later applications. You then have surface blasting machines, very similar to depowdering. The main difference is instead of removing powder, we're trying to reduce the surface roughness, the RA, of the parts. So we do this by firing plastic beads at high pressures to reduce those layer lines. And finally, the one we're going to speak about mainly today is the vapor smoothing. Vapor smoothing is essentially a chemical process which is sealing and smoothing the parts to enhance the performance of that end product. You'll see quite a lot of different machines listed on this page. Within each section, essentially, the machines vary on size and requirements based on what the customer needs. So on the next slide, there's a quick video. It's going to go through the vapor smoothing process. It's a lot nicer than listening to me talk for 2 minutes, and hopefully it covers everything on that. So you can play the video for me. Okay, so now you've seen how the vapor smoothing kind of works. If you have any more technical questions, Simon and the guys at Evoke will be able to talk you through it. But I'd like to talk a little bit about the technical testing that we've done with the post-pro SF machines. So one of the studies I thought I'd talk about was one we did with HP, obviously with Clara being on the call. So this one was focused on PA12 and TPU parts, so specifically BSF TPU. And we did a series of tests using dog bones, standard test parts, and these were all done in accordance with the relevant ISO test. So it's important to note with all these testing, there was no additional processing or pre-processing steps. All that happened was the part was printed, it was unpacked, depowdered and smooth. We didn't tumble or die or anything like that. So you can see here the results for the PA12 and the TPU. So there's significant improvements in the surface roughness, that's significantly reduced, tensile strength and elongation at break. And also what a lot of people are concerned about is changes in the dimensional accuracy of the part. So in both materials, you can see it's only changed by 0.4%, and it is well within the printer tolerances of these parts. The reason you see dimensional changes is not because we're adding or removing anything to the parts. Essentially, what's happening is we're reducing the height of the peaks and we're increasing the height of the troughs, and it's leveling it out and creating that smoother characteristic of parts. On the right hand side, you can see a couple of examples of these parts. So you've got the grey part or the greyer part, and then the black part. So nothing was done apart from vapor smoothing, and that black color is the inherent color of the additive that HP use for this printing. Next slide, please. So a quick summary of the figures again. So surface roughness reduced by over 90%. You have tensile strength increased by 8%, and then elongation at break by 10%. So obviously, being a sealed surface, it becomes a lot more sterilizable. You can clean it. It's not going to be absorbing materials like water and sweat and so on. And aesthetically, of course, it looks nicer. You saw from the previous slide that the grey parts turn black, so there's no need for dyeing for certain applications. At the bottom, we've got a couple of microscopic photos, on the left before, on the right after. So on these materials, you can see the before, there's porous, you have some microfractures, and then there's obviously a lot of space for contamination of things to occur. And on the right hand side is the after. Again, it's a lot smoother, no porosity or anything like that. In the top right hand corner, this carries on a little bit from the porosity. So the blue line shows the as printed part, and it shows over time the weight increasing as more and more moisture is absorbed into the part. And then at the bottom, of course, once it's sealed, it's not porous anymore. The weight remains the same. Next slide, please. So I thought I'd just talk about a few case studies we've done relative to the O&P world. So the first one, Simon's already spoke about, the company Ability Made. So we did a study with them using their PA12 MJF material. The main findings were high gloss finish, so they improved the aesthetics and the appearance of the part. And then they found it encouraged user use. So if it looks nice, they're more likely to use it, of course. With the reduced RA value, of course, the friction is a lot less, so you're seeing a lot less friction injuries. And of course, the cleanliness has also improved, being sterilizable. Additionally, with the AFOs, they found that the higher impact strength created by the vapor smoothing was very important for the design of the part. They could change the design slightly to save on materials, save on printing costs, and so on. But also, they found that the sharp shards that were the common if the AFO were to fail didn't occur after vapor smoothing. So without the shards, without the sharp edges, you're reducing the risk of injury to the patient should it fail. Next slide, please. Next, we have Proteo. So Proteo are a prosthetics manufacturer, and they use our vapor smoothing technology to enhance their 3D printed duo socket prosthetics. So essentially, this is a PA12 outer and a TPU inner. The reason they looked at vapor smoothing was they were looking for a more comfortable, durable prosthetic. In this specific example, the patient was very active and they wanted to take up sports like football and cycling again. And with the vapor smoothing, they were able to do this. With the sealed prosthetic, they could clean it down after use, so there wasn't any sweat or bacterial growth because of it. And the strength of the prosthetic was strong enough for them to use for a prolonged period of time without the risk of it failing. Next slide, please. And then the last one is Invent Medical. Clara spoke about these guys before as well. So the one I wanted to focus on was the Tally helmet, protection helmet that they use. So again, a 3D printed orthosis, and it's used in adults and children who have undergone cranial surgeries, or they need some additional protection from falls. Maybe they suffer from epilepsy and so on. So with the vapor smoothing, it offered an additional 40% more protection than conventional products. It also maintained its durability and hygiene in making it safe and easy to use. Because of the target market of this product, aesthetics are very, very important. So it's primarily used with children. They print in white SLS, but they dye vibrant colors, so you can have blue, pink, red, whatever you want. So visually, aesthetically pleasing parts is very important because the children won't put it on otherwise. With the vapor smoothing, you can dye before or after, and it enhances that color. So that was really useful for them. And then one last thing about the Invent Medical, because of the use being in contact with young children, they wanted to ensure the parts were safe and could still be used after vapor smoothing. They didn't want any traces of solvent. They wanted it to be as printed and no concerns with regard to patient safety. And that nicely leads us on to the next slide. So on the next slide, we have a summary of all of the standards and the tests that we've carried out on the materials. So you see there's a lot of different materials, a lot of different printing technologies. Some related to safety, some more related to the technical suitability of the parts. So we've passed things like skin irritation, sensitivity, cyto, to name a few. The main takeaway from this is whenever the parts are processed, all of the consumable used to process the parts is removed during the machine. So the part is the same coming out as it went in. So there's no safety concerns there. So all of these tests, they were done using the post-pro machines, and there was no external cleaning or drying done. So it's into the machine, out to the machine, ready to use. And just onto the last slide, please. So just a quick conclusion, you can see a few of the applications here. Essentially, the vapor smoothing significantly enhances the surface finish. You're getting improved mechanical properties, and it encourages users to use O&P devices more and more, thanks to the aesthetic improvement. The solutions ensure the parts are not only functional, but also ensure a faster recovery because patients are more willing to use them. I've only covered a few of the applications in one white paper, but there's a lot more on our website. So if there is anything you're interested in, maybe we're looking at a slightly different application, I'm sure there'll be something on our website that's more relevant. And if in doubt, Simon and the guys at Evoke can point you in the right way. But that's it from me. Thanks very much for your time. I'll pass you back to Joe to close it off.
Thanks, Sam. Much appreciated. So just before you head off, and as we move into the questions section, we do have and if you could please, if you've got any questions bubbling away there, if you could please post them up in the Q&A chat right now, that would be great. We've got 6 minutes to get a few questions in. So first question for you, Sam, coming in here. Is it the same chemical that's needed for different materials, PA12, TPU, PP, etc.? You know, what's the nature of the chemical?
Yeah, so the materials we can do. The first part was about the materials we can do with the consumables. So we have 3 main consumables. We have our standard commercial consumable, and that can smooth over 150 different thermoplastics, including PA11, 12, TPU, all of the main ones. We then have a dedicated polypropylene solvent, and that will work just for the polypropylene parts. It won't work for your PA12s or anything like that. And then the third one is our green solvent, and that's focused on customers who are more mindful of the environment. They want a greener solvent, a less hazardous solvent that they can transport easier and worry about less the safety of in their facility. And the compatibility of that, of course, is a little bit less. TPUs and PA12s tend to still be okay. With regards to the chemical itself, it's a low boiling point alcohol. They're three different chemicals, but essentially low boiling point alcohols, just so we can vaporize it, smooth the parts. It needs to obviously react with the material and then take it away after.
Thanks, Sam. And just to reiterate your slide there, it is a closed loop process, and so those chemicals are contained within the machine, and obviously they're not released into the environment at all. So just to be clear on that. I had another question actually, which is around, automation. What are you seeing with automation of, your processes, loading and unloading and that sort of thing? Is that coming?
Yes, I mean with P&O stuff, obviously the parts tend to be larger than other industries. So typically these are hand loaded, but we do have automated solutions. So we have things called a DMS system, an auto loading robots to load the machine. So essentially you can have lights out manufacturing if your volumes permit. Of course, if you're only doing 50 parts a week, maybe it's not suitable, but we have high-end users. We have customers in the US that have completely automated systems, which you put the parts on and it will automatically load the racks, put into the machine and unload. So it can be lights out manufacturing if you want, but of course it depends on throughput and cost really.
Right, great, thanks for that. And got another question here, probably throw to you, Simon. A little bit of chat going on around capturing those pressure maps or those fields to input into the NTOP. Can you share a little bit with ways to capture that data?
Yeah, sure. There's a couple of ways. So one is the example which I showed, that was actually based on a university study done in conjunction with NTOP. So what they did is they did instrument a seat, a bike seat, just with strain gauges, etc. And with that strain gauge, they were able to sort of develop a pressure map. There is actually, that idea, that concept has actually been commercialized. There's 3 companies currently printing seats. So there's Physics specialized, but there's one out of the Czech Republic called Prosthetic. Now, what Prosthetic do, that they are the only ones that are actually the 3D printing that are unique to the customer. And what they actually do is they send you out a pad which you physically sit on, and from that they actually scan that and take the deformation, and then they use that to generate a mesh structure to suit the shape of your derriere.
There we go. So look, really interesting area in O&P, and I think capturing the the distribution of load across a a residual limb, it's a really interesting area. So yeah, watch this space. Okay, got another question here actually for Clara, which is just wondering, with your sort of global overview, how are you seeing adoption of direct digital manufacturing in different regions around the world? Is there sort of some regions are sort of more readily adopting it than others, and do you have a sort of feel for that distribution?
In the O&P space, honestly, Australia was one of the early adopters of moving from traditional to digital, and I think there were several companies that adopted and kind of accelerated this move. In terms of worldwide distribution, as I said, it depends on the material. That's where I see differences. In terms of adoption, I cannot see there's a difference between Europe and the US. What we do see is, especially in the last year, the growth coming from adoption in O&P is huge. It's probably from all the segments that we serve, from like automotive, industrial, dental, O&P is the one that's growing the most. And I think it's because if we go back to like 2017, still there were too many things to figure out, especially on the workflow side. Now there are a lot of solutions that are putting this transition from traditional to digital a lot more smooth, and I think that's accelerating adoption. Actually, this week, today, OT World is starting. That's the biggest O&P show in Europe, and I mean, you walk the floor and it's full of additive parts.
Yeah, interesting. Great show, and I know quite a few practitioners from Australia are over there. Good on them. So we'll wrap up there, and thank you everyone for your time, and thank you to the presenters. Just quickly, if you would like a free sample of a printed vapor smoothed mini AFO, thanks to Masson's Healthcare, who represent Invent Medical in Australia, by the way, please reach out to us and we can organise that part to be delivered to you. If you'd like a live demo of the end topology software or more information about that, same, reach out. And of course, if you want to see our webinars on the Evoke 3D YouTube channel, please go to @Evoke3DAU and yep, like, share and follow. That'd be appreciated. Thank you and have a great day.